Good morning everyone. In this lecture of the lecture series, I am going to talk about the topic of constrained extremization. Okay. So, namely I am going to introduce one such constraint, namely the isoperimetric constraint. So, before I do that, let me just talk about the different types of constrained extremization that we are going to talk over the different lectures of this course. So, we could either have a functional that we want to extremize, plus we also have integral constraints, right, say constraints of the form integration of g of x y y prime dx, which is also equal to a constant. So, if we have constraints of this form, I call this class of problem as my isoperimetric problem, isoperimetric problems, right. Okay. And then I also have I can also have functionals plus some algebraic constraints, problems having algebraic constraints, and in that case let us say we have the constraint of the form g of x y equal to 0. The problems of this class we will denote them by the holonomic problems, right. The problems having constraints which are purely algebraic are the holonomic problems, and finally the problems in which we have differential constraints. Differential constraints we have of the form, we call them as the non-holonomic problems, right, non-holonomic problems. And today in this lecture course, I am going to talk almost exclusively on isoperimetric problems or problems with functional optimization with integral constraints. But before I talk about isoperimetric problem, I need to introduce some basics. So, again to discuss about the basics, we have to go back to our finite dimensional or multivariate calculus. So, let us now revise some of the basics and look at the various concepts that have already been discussed. Well, part of them are already been discussed, but part of them are now going to be discussed in finite dimensional calculus. So, finite dimensional constrained function optimization. Okay. So, now people who are familiar with this finite dimensional constraint function optimization, they know that one of the standard way to perform this optimization is via the method of Lagrange multiplier. So, we are going to revise this method, and to do that let us start with the very basic constraint problem, namely problem with one constraint or single constraint problems. Okay. So, what I am saying is the following. Let us start with our discussion with the single constraint problems. Okay. So, the problem here is to determine, we have to determine local extrema, determine the local extrema of the function f from, let us say, R2 to R. So, I am taking a function of two variables, just to simplify, subject to the condition that f is sampled on gamma, which is a subset of R2. Okay. So, then suppose that my subset gamma can be defined with respect to some parameter. So, suppose gamma is defined parametrically. Gamma is defined parametrically by gamma of I to R. Let us say I is, well, yeah. So, I is a subset of the real axis. So, my parameters are all real numbers. So, suppose gamma is defined parametrically, let us say by gamma of t is equal to x of t comma y of t. So, gamma is a function from r to r square, where t is in the interval I, which is a subset of r. Okay. So, then we allow, in this problem we allow f, our objective function from R2 to R, to be constrained on gamma, by the following function capital F from I to R, by the function f of t is equal to f of small f of x of t y of t, right. So, the moment we say that f is constrained with the condition gamma, then all the argument points of this objective function small f has to be picked from gamma, right. So, then my necessary condition for local extremum, at point t is given by d dt of f of t is, well, I am just using the chain rule to see that the derivative of capital F, f of x prime t, where the prime denotes the derivative with respect to t, plus f of y prime t. To find the local extremum, this must be set equal to 0. So, that is the basic criteria for the constraint optimization, where the points are picked from the constraint set gamma, and then the problem then reduces to that of the unconstrained version. Okay. So, let me call this boxed relation as 1. Okay. So, then few other issues to be highlighted. Note that the curve gamma must, let us say we represent the curve gamma, the gamma is the constraint curve, by some function. Let us say we represent the gamma represented by an equation of the form g of x comma y is equal to 0, right. So, which means that if g is smooth, when I say smooth, then it means that the derivative exists and they are non-zero, right. So, the gradient of g is non-zero, that is what we are assuming. Then my condition g of x y could possibly be solved to represent one variable y with respect to the other variable x, right, could be used. So, the idea is, it seems that my constraint problem can be reduced to an unconstrained problem through the use of the constraint g of x comma y, and I am just writing some of these steps, but the question is it really true? Can we really represent or change the constraint problem into an unconstrained problem without suffering any setbacks? So, this question is something that we will answer over the course of time. So, let us say now, so g of x comma y could be used to solve for one variable let us say, right, one variable as a function of the other, right. So using g equal to 0, I can very well express y as a function of x. That is something I am assuming, and if that is the case, then the constrained optimization of two variables, the constrained optimization of two variables reduces to the unconstrained optimization of one variable, right. Okay. It seems the picture is very rosy, right. There is no point in talking about constrained optimization, at least in finite dimensional calculus, but certainly it is not true. We can encounter many problems. So, let me list some problems in this methodology, right. Well, the first problem is obvious. Not necessarily we could solve g of x comma y equal to 0 to represent y as a function of x, right. So, finding explicit solution of g equal to 0 may not be possible or convenient, I would say convenient, right, at least analytically. And then the second problem is even after solving for g equal to 0, the resultant solution may not be smooth. The resultant solution may not be smooth. Resultant solution may not be smooth, right. Let me just highlight this particular case, this problem. Example, let us take g of x comma y is equal to x square plus y square minus 1. So, let us take this function and this constraint as follows. So, this constraint is all the points x and y which lies on the unit circle, on the boundary of the unit circle. Okay. So, this, although this is smooth, this constraint is smooth, that is, we can find the derivatives of g with respect to x and y, and they do not vanish on the boundary of the circle, right. But solving for g, so what happens when we solve g equal to 0? We see that I get y, we definitely get y as a function of x. So, I am just showing the positive branch. We see that y as a function of x is not smooth at certain points. So, this is not smooth at x equal to plus minus 1. So, this is not smooth at x equal to plus minus 1, right. Okay. So, the alternative is the method of Lagrange multiplier. The alternative to avoid all these problems is to use the method of Lagrange multiplier, right. Okay. Well, we will see that even this method encounters some problem, and we are going to segregate those class of problems, right, also known as the abnormal problems. But let us look at the normal problems first. So, suppose f is smooth, and the curve gamma which is the constraint on f, the curve gamma which is the constraint on f is defined by a smooth function given by g of x comma y equal to 0, right. And I have that further gradient of g of x comma y is non-zero, right. The gradient of g of x comma y is non-zero. We need that, otherwise we will run into trouble, as we will see later on. Okay. So, let me call this condition as star, right. So, we are also assuming g is smooth or the gradient of g is non-zero, right. So, let me also further define gamma by a smooth vector. I define my gamma as a smooth vector r of t equal to x of t comma y of t, where t is in I, such that r of t is not 0, right. For all t, r prime t is not 0 for all t in this interval, because if it is 0 for some t, which means both x of t, x prime t and y prime t are 0, and then we will not satisfy this starred condition, that is the gradient of g is non-zero. Okay. So, I am given, so since it is given that I have the constraint g of, well, so g is the constraint, right. So, I am representing the constraint with respect to the parameter t. So, it is given that this constraint is 0, right. So, for all x of t comma y of t in gamma, right. Okay. So, from here what we get is that the derivative of g with respect to t is del g del x x prime t plus, just using the chain rule, del g del y y prime t, right. Okay. So, let me call this as 1, and also I have that the necessary condition, well, let me call this as 2, because 1 is sitting somewhere else, right. So, we see that the necessary condition for an objective function to be having an extrema is this following. So, let me rewrite again. So, let me call this as 2, because 1 is the following. We know that the necessary, well, let us keep it in proper sequence. Let us call it as 1 itself. So, we also know that the necessary condition for local extremum of f on gamma gives us the following condition: f of x of t comma y of t is equal to f of x x prime t plus f of y y prime t. This is also equal to 0. So, that is my necessary condition for the extremum to occur. So, I am going to call this as 2, right. Now, we know that the gradient of g from star, we know that the gradient of g does not vanish, right. So, which means, so look at this quantity 1. So, in 1 I have used both the derivative of g with respect to x and y. So, we assume that, so either it turns out that either g of x or g of y are not 0, or both are not equal to 0. Either one or the other, both of them are not equal to 0, right. So, suppose, because otherwise we will have a contradiction via the star, the condition star, that is the grad g is non-zero, right. So, either one of them or both of them are non-zero. So, let us assume, we assume without loss of generality that one of them is non-zero, right. So, let us say that g y is non-zero, right. So, which means from 1, the 1 can be changed into another relation, that is y prime is equal to negative g x by g y times x prime of t. So, let me call this as 3, right. So, I have represented one derivative with respect to the other derivative. Now, so now let us use this relation using the previous relation 2 and 3. So, I am going to find out a common relation between f and g. So, relation 2 is as follows. So, in relation 2 I am going to substitute this expression for y prime using relation 3, and I see that I arrive at the following expression. So, x prime t by g y of f x g y minus f y g x is equal to 0. Okay, now, so either we have that x prime t is equal to 0, or we have that this bracketed quantity is equal to 0. Now, I am sure it is clear that this is not possible. This condition is not possible, because if x prime t is 0, then from this relation I can immediately see that y prime t is also 0, or it tells me that the derivative of the curve with respect to the parameter t is 0, and that leads to a contradiction via our result star, where we say that the gradient of the constraint is non-zero, right. So, we lead to a contradiction. So, certainly only this is possible, right. Now, what is this condition? This condition is nothing but grad f cross product with grad g is equal to 0, right. So, we are talking in 2D, So, this is the grad of f cross product with grad g is 0, or in other words I am saying that it is equivalent to saying that grad f is parallel to grad g. Grad f is parallel to grad g, or what I am saying is the following. So, let me rewrite this statement. What I am saying is that the vector grad f is proportional to the vector grad g, and this is the primary statement of the Lagrange multiplier condition. Okay. So, this is the necessary condition for extrema, okay, or where my constant of proportionality is my Lagrange multiplier or the LM method. Okay. So, then Lagrange multiplier method. Okay. So, then let us look at an example to see how this method works, right. So, notice before we go ahead, notice that the Lagrange multiplier has introduced another constant, that is an unknown constant lambda. So, how to evaluate this extra constant? Well, the answer lies that we have also the constraint g equal to 0, and that will take care of this extra unknown, right. So, let us look at an example. So, find the local extrema, for the function defined by f is equal to x square minus y square, right, subject to the condition g of x y is x square plus y square minus 1 is equal to 0. So, we have to extremize this function subject to the fact that x and y lies on the boundary of the circle, unit circle. Okay. Well, we can directly start with the Lagrange condition. So, the necessary condition is the grad here the grad will boil down to the two dimensional derivative. The grad of f minus lambda g is equal to 0, right, or this means that the grad of x square minus y square minus lambda x square plus y square minus 1 is equal to 0. Okay, so from here when we take the necessary derivatives, so with respect to x, when we take the derivative with respect to x, I see that I get the following equation: x 1 minus lambda equal to 0. With respect to y, I get the following equation: y 1 plus lambda is equal to 0, right. So, let me call this as 1 and this as 2. Okay. So, now we have three unknowns x, y and lambda, and then the third equation is this constraint which solves for the third unknown. So, to find the solution, notice that from 1, so from 1 either x is 0 or lambda is equal to 1, right. So, if x is 0, I can plug the value of x equal to 0 in the constraint. So, from the condition g equal to 0, I get that y is equal to plus minus 1, right. Notice that x equal to 0 and, well, if y is equal to plus minus 1, we get one such point, right. Now, we have not spoken about what is the value of lambda. If y is either of the values plus or minus 1, I get from the second equation, I get that lambda is equal to minus 1, right. So, one such, so let me, so this is this or this, right. So, one such point or two such points that we have found from this exercise is 0 comma plus minus 1, and the other equation that can be found, other solution that can be found is by assuming lambda is 1. So, if lambda is 1, so if lambda is 1, then x must be, well, to have lambda equal to 1, we must have that the second equation is satisfied only when y is 0, right. So, we get, it implies that y is 0 from 2, and putting this in the constraint. So, from my constraint I get that x is equal to plus minus 1. If y is 0, x is plus minus 1, and the second set of solutions that I am getting from this exercise is plus minus 1 comma 0 with lambda equal to 1, right. So, lambda equal to minus 1. Okay. So, then, so that this example clearly highlights the applicability of Lagrange multiplier method, right. So, then let us now state this result of Lagrange multiplier in the form of a theorem that we are going to use frequently. By the way, Lagrange multiplier can be extended to higher dimensions, right.